Okay, people. Can you see my screen, my PowerPoint screen?
Yes, but not full screen.
Okay. I'm going to work like this only. Okay, so these are the three topics that we're going to be working in this chapter. Okay, vibration of systems with 1 degree of freedom. And then we're going to separate free and forced vibration of systems with several degrees of freedom. Okay, so let's start by, I'm not going to solve all of that. I'm just going to highlight some of the main characteristics of the problem, that's all. Okay, what's the degree of freedom, people? What's the degree of freedom? Anybody? Or let's go in order. Let's keep going in order. Miss Freire, can I ask you something? Can I ask you a favor, people? When you define your profile, could you please change your profile and put first the last name? So, because right now I can see, for example, Arnold Manrique, Alison Pincay, Stais Freire, etc. But I could have them in alphabetical order, but that would be much easier for me to keep track of the participants. Okay, so if you, for the next session, would you please allow me, help me with that, okay? So change your profile and first include your last name, if possible. Okay, Ms. Freire, do you remember what the degree of freedom is?
Hi, doctor. Is the number of, like, the number of systems in, no, the number of movements that a system can do, or more or less.
Okay, something like that. Or a number of functions, okay, that are needed, describe the motion of a system. Okay. So in this chapter, or in this subchapter, we're going to start by considering systems with 1 degree of freedom. That means that in this case, in this subchapter, we're going to be trying to find one function, of course, dependent on time. And if you know that, you know exactly the position of the point of the system. You can describe how it moves. Okay, and the way we summarize this, remember, is using this classical sketch. So we have a restoring spring in this case. For example, in the case of a ship, if you push downward, you're going to have more buoyancy than you need. And that extra buoyancy represents the effect of the spring. There's no spring, it's just a similar effect, the restoring effect, okay? And for this case, we assume that no mass. Okay, this is a very delicate problem, the damping. And it's also a dissipation of energy. Okay, this is like its description. It's also massless. There is no mass. This is the mass. Since this is a 1 degree of freedom, we assume that it's a point mass. Remember, in AutoCAD, when you have a point, you cannot rotate it. So if you have a mass which is very small, the only motion that you are going to be worried is the vertical displacement. And remember, this is a 1 degree of freedom system. Okay? So on the mass, we have also an excitation. Okay? So if this is the displacement, we call it W of T, okay? The excitation we consider, which is independent, okay? So in the restoring, in the damping, and the acceleration, we have influence from W. The excitation is independent, okay? So mathematically, we're gonna have 3 terms on the left and 1 term on the right. The terms on the left include W or its derivatives. The term on the right is independent of W. That's why we put it on the right, okay? Remember, anybody remember, Miss Hidrobo, do you remember what does the fact that this device doesn't have mass? Is there anything special about that? Do you remember from vibration, mechanical vibrations? When something doesn't have mass.
It doesn't have mass, is proportional to the displacement, to W.
It has to be, no. It doesn't have mass. For example, similarly with the damper. If something doesn't have mass, it has to be Mr. Jürgen, Mr. Ramon. Mr. Ramon?
I'm here, doctor.
Yeah. If something doesn't have mass, do you remember?
It's not we have infinite oscillation.
No. Okay, don't worry. If there is no mass of something, that means that has to be in static equilibrium. So if this is connected to the foundation and this is connected to the mass, okay? So the force exerted by the foundation on this point and the force exerted by the mass on this point on the spring, they both have to cancel each other. Because summation of force is equal to, has to be 0. Because there is no mass. If these two were not equal to 0, we will be in trouble because the acceleration will be infinite. And we don't want to work with those kind of systems, all right? Okay, so that. So both has to be in static equilibrium because we assume them to be of very small mass. And after this, this is something which is very, very, very important, is that this is measured from the static equilibrium position. So before that, the weight and the static elongation of the spring, they cancel each other. When you put a ship on the water, reaches its draft, reaches its stream until finds the static position. And from there, you can start considering that it can move vertically, but that motion, vertical motion, is measured from the static equilibrium position. Okay? So that's W, and this is what we're going to be calculating in this class. The equation of motion results from applying remember, this is the acceleration, the center of gravity. And from here, we can deduce that mass and the excitation, we take it as an harmonic excitation. So it's going to be an amplitude e to the I omega t plus a phase shift beta. So we know what M, C, and K are. W is the displacement measured from the position of static equilibrium, velocity, acceleration. On the right-hand side, excitation. This is the amplitude of the excitation. This is the frequency of the excitation. And in general, we have to include a phase shift, beta, in general. In shift dynamics, it's very interesting because usually we start by taking as a reference the level of the surface. But the level of the surface has to be transformed into excitation force, which is going to be acting on the system. So there can be a phase shift, a beta, between the force and the surface elevation. Okay, so the surface elevation could be a cosine, amplitude times cosine, but that has to be integrated, or that generates pressure integrated on the whole surface and generate a force. So that force can have a phase shift with respect to the elevation of the wave. So that's, in general, that's something that we have to include in our calculations. So it's a good idea for us to include it. Now, here, we still have a couple of minutes, we can separate free and force it. And in free, we have no damping and damped oscillation. What's the main characteristic of the free oscillation? Anybody? Mr. Delgado, if somebody asks you to solve a free vibration problem, what's the main thing, that's the main parameter that you have to calculate in the case of the free oscillation? Anything that comes to your mind? Free oscillation.
I don't remember.
Don't remember? Mr. Galarza, do you remember?
It will be the natural frequency.
Exactly, yes, natural frequency. So it oscillates, but according to the parameters of the system, the characteristic of the system, that will be an oscillation with a certain characteristic, and that characteristic is the natural frequency. So, Ms. Michelle Lopez, do you remember the natural frequency in the case of the damping, the no damping case?
The square M over K.
No,
K over M. Sorry.
No problem, no problem. Okay, in case of damped, okay, in case of damping, there is no excitation and we consider no damping. In case of damped, there is no excitation. So in this case, in the damped case, we consider the three terms on the left. The solution in this case, remember, is e to the minus z omega 0 t, and then we have a constant, and then we have the cosine omega damped time plus a certain, let me change. Let's use another. Okay. And what does this tell you? Mr. Barba. Mr. Barba, what does this term tell you?
I don't remember, doctor.
Come on. Miss Vega? Miss Vega? Do you remember this term? Any comment about this term, Miss Vega?
And the resonance.
No, no. Resonance is down here when we talk about forcing. Up here, this term, e to the minus z omega 0 t. Miss Matias, this term, what produces this term? Miss Matias? Problem with connection. Mr. Carrillo, you remember this term?
Sorry, doctor. It is reduced. This is harmonic.
Yeah, no,
The oscillation.
be more specific, please. This is a real term, negative. So what this does is dies out. So what happens is that the oscillation is reducing until finally dies out. See, so as you increase the amount of damping, as you said, Carrillo, this term takes this, reduces the whole solution, and then finally comes back to its neutral position. Okay. Okay. Before we break up, is there any questions about this? Would you please raise your hand, those of you who are out from outside the city of Guayaquil? Can you raise your hand? Gutenberg, you should raise your hand.
Sorry, your question is the people that not stay in Guayaquil.
Yeah,
right?
but okay, but we can consider that you are not Mona. You are from.
But I thought
I'm joking. Don't worry. If you want to be Guayaquileña, that's fine. That's okay. We don't. I mean, this. Mr. Ramon, you're from Machala. Come on.
No, doctor. I'm here in Guayaquil.
I don't care. You are from Machala. Raise your hand. Miss Matias, you are from La Península, I think, right? Mr. Carrillo, you are from Ambato, Riobamba, right?
Riobamba, doctor. This
Okay,
is moment
raise
I
your
hear
hand.
reading.
Raise your hand. Raise your hand. Miss Matias. Miss Vega, come on, Miss Vega. You're from Sayo, you are from Guayaquil. Yes. Okay, we have 3, 5, 7 people. Carrillo, you are from Riobamba.
Yes,
Okay, so
doctor.
we have enough people from outside the cities. So at least we have one person from outside in every group. Okay, let me identify. Please, down your hands. Lower your hands, please. Now, let's have our hands up, the ladies, the women. So I can see if we have enough women to form each one of the groups. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have 9 women, so plenty. Okay, so every group will be able to include at least one person from outside Guayaquil and one person from so please start getting in touch with other students. At least the first two homeworks are going to be individual. So the first one is going to be about vibrations. The second one is going to be about hydrodynamics. Both have to be completed individually. Okay, is there any other question, people? So I'll see you, if there's no question, then I'll see you Thursday at 4 p.m. Okay, if you're interested in getting a copy of the class notes, don't forget to send an email to Ms. Kinder. Bye-bye now.
Thank you, doctor.
Okay.